Okay, why don't we get started? Got most of the people here. Can everyone hear me?
Yep, we can hear
okay,
you.
and it's displaying this, all right, thanks. Let's see. So last time I started going through how you define a polymer, or in other words, how a polymer is kind of defined from a physics perspective. And one of the main ways is through rheology. So I showed you some examples of different polymer flows, like this kind of teardrop shape bubble that will form in a polymer fluid, polymeric fluid. And then I showed some of these, I showed like rheology curves, right? So I wanted to show you what a rheometer looks like, what an oscillatory rheometer looks like. I found this video, that looks, well, at least goes through what the rheometer looks like. It's kind of an entertaining, pretty good video, but so let's see, let me just, all right, so he's just going through yield stress materials in this video, but I wanted to show the machine. If I can get this, all right, so this is a rheometer here. Let me just, so he's putting like mayonnaise into it. So it's kind of an interesting video, but so basically it's an oscillatory rheometer. So you can turn this top disc will turn, okay? You can turn it continuously in one direction, and the bottom disc is fixed. The bottom disc has some kind of heating plate on it, or there can be an oven that encloses the whole thing. And then the way this is set up, let's see. Let me shrink this down a little bit. So the way it's set up is like this usually. So you have a plate geometry, or you can have a cone and plate. Okay, so the cone and plate is going to have a very weak angle. So this angle of the cone on the top is going to be like 1 to 2 degrees. So you wouldn't be able to see it with your eye. And the bottom plate is flat. Okay, so the reason is if this thing spins, right, then the velocity at any point along this is going to be proportional to the position, like the radial position, right, because it's going to be related to the circumference of a circle, which is going to be proportional to the radial position. So if you have a gap that increases, so your gap distance, D is going to also be proportional to R if you have a constant slope. D is also proportional to R. Then the strain rate is going to be the velocity over that gap. So basically V by D, so the R part cancels out and you get a constant strain rate, which is what you want. You're gonna plot the viscosity versus the log of the viscosity versus log of the rate of strain. So you want to have a constant strain rate across the gap, or you'd have to integrate across the different strain rates that are in the gap. All right, so to have a cone is like the ideal setup for this. Since the angle is so small, then people just use a plate. It's somehow easier. Okay, so the problem with the cone is you'll get slip. You can get slip features at different gap lengths. So sometimes for a viscous fluid, plate geometry is used. But ideally, you'd use a cone and plate geometry, and then you can get a constant shear rate across the gap. That way, you can make this plot reasonably. Otherwise, it's an approximation. But here he's using mayonnaise, and he puts jelly into it, and he uses a plate geometry, which is pretty common, but usually the cone and plate is the thing that people want to look at. And then hopefully you guys can see this. And then this thing, he's also using a constant a constant strain. So he's just turning this thing continuously, right? So he's got a constant strain rather than an oscillatory strain. Okay, so this is a little bit different because he's doing yield stress. Anyway, this thing you can find on the web page. That web page. Sorry. On the web page for the class, I just put a couple of videos up of rheology if you want to look at it. Where did I put those? I put them right here. So like yield stress. It's kind of an interesting video to watch. It's about 5 minutes. But I don't want to waste the time now. This Christmas Costco video. He's from Minnesota. I think he's retired now. You know, basically he goes through the entire polymer rheology in about 30 minutes on a video, which is kind of useful. There's some other rheology things to click on here. I just kind of piled up a few of them. These are mostly I teach this class polymer characterization, and in that down at the bottom is a rheology, oscillatory rheometry lab. So there's a bunch of links there that you can look at. One is this link to Southern Mississippi, which has, oh, that's a DSC thing. Sorry, that's someone asked about DSC. That's the DSC thing. Anyway, there's a bunch of links to rheometry in that section in that course. Anyway, so the point of this is last time I went through, if you have a Newtonian fluid, the viscosity is constant with shear rates. It doesn't matter how fast you turn. So it's basically there's a continuous strain, and this you could do by just turning the top disk continuously. And then normally this is an oscillatory operation. So you're going to oscillate this thing. Okay, and the oscillation is going to be something like 60 hertz. Right, so maybe between 1 hertz, so one oscillation per second, and maybe 300 oscillations per second. So typically, like the 60 hertz, which is like the AC hum, like bah. So this thing's going to make an acoustic kind of vibrational sound when it runs. Right, so, and the strain amplitudes, the amount that you turn this thing, is going to be about like 1%. So it's basically not moving much to look at. It's vibrating. So this thing's really just vibrating to get the rheology. Okay, and that's the normal way to do a polymer rheology, because if you strain it too much, you deform the fluid. So you don't want to deform the structure of the fluid. You want to have a low strain to maintain the fluid undeformed. Right, so basically, an oscillatory measurement with a 1% strain at something like 60 hertz is kind of the normal thing that's going to happen. And this thing's going to be a sinusoidal vibration or rotation of that disk. So you're going to think about the strain, this shear strain. So basically, this, if you kind of blow this up, you'll have like a y direction here and an x direction here. Right, so in the bottom plate it's fixed, and the top line is really this top disk surface. Right? And then the fluid, and that's going to follow, it'll stick to the surfaces, so it's not moving at the bottom, and it's moving with the velocity that's got a time dependence at the top, that's oscillating in a sinusoidal way. So if you look at the profile of this is going to be a straight line, and the slope of the straight line is a dV dy, which is the slope of the straight line is the strain rate, gamma dot, if this is a velocity profile. And so that's kind of the idea of this. And then you're applying a force to the top to make it turn. And then the force per the area that the force is applied is a stress, the tau xy. So the force that you apply is related to the speed you get out of it by the viscosity. So you have that kind of relationship. Right? So you can get this viscosity. You can change the rate of oscillations to change the frequency. So this is kind of the frequency, like log of the frequency of vibration of this thing. And if it's a Newtonian fluid, like water, then this is just flat. It doesn't change viscosity. So the force is proportional to the motion. And it's linear. But if it's a polymer fluid, so it's a shear thinning fluid, then this thing drops. Like it has a power law. It's logs is the power law. To end up the viscosity goes to the strain rate to a power. And that again is because the structure of the material changes. In the structural change, so say you can take a coil, a polymer coil, and you can deform it, and then it can go back. That takes a certain amount of time, tau, right? And 1 over that time tau is going to be this strain rate. So once you reach a strain rate below that, the deformation, the coil can return. So viscosity doesn't change due to deformation. When you deform it above that frequency, it doesn't have enough time to return. So you've changed the fluid. And because the thing kind of orients in the direction of flow, then it's going to flow easier versus a tangled mat of spaghetti. This would be like uncooked spaghetti. So the further you go out on this at higher rates, the more uncooked the spaghetti gets and easier it is to flow. And that follows power law dependence. Right, so this cutoff point is going to be a relaxation time, and that kind of behavior only happens with polymers. Right, low molecular weight or oligomer will only have this flat behavior. That's kind of the point. We went through that last time, more or less. Any questions on that? I mean, it's kind of complicated. We'll go through more rheology later on, but basically, if you have any questions on that now, it'd be good to go through it if you want. But all right, so that's the easiest and the most common way to describe a polymer is by the flow, right? Simplest thing you can do. Shear thinning is the typical behavior, and these I mentioned also that normal stresses develop. So there's going to be a force inside this oscillatory shear instrument that goes normal to it. So you can measure this normal force. So as you shear it faster and faster, a force develops that wants to push the thing apart to expand the gap. Right, and that you don't get a normal force in a Newtonian fluid. That normal force is coming because of this same mechanism. So because it springs back from this stretched out to this kinked up, then you can see the size changes and a force develops here in normal direction. Right. Guys, unless you want to talk. If anyone wants to interrupt, that's good. You know, the more interruption, the better. But all right. So anyway, that's kind of one part to define like what a polymer is from a kind of a physics perspective. So this is Flory talked about. So this has got to do with fluctuations. So this is a picture of thermal fluctuation. So space is filled, like some temperature in the room, 20 degrees C, but in any position within the room, there's hot spots and cold spots. There always are fluctuations in the temperature in any material like air or wood or metal or plastic, right? So everything's going to have fluctuations in temperature, which means that molecules are moving around faster in the hot parts and slower in the cold parts. It's this idea of thermal fluctuations, more or less the basis for thermodynamics. Like the idea that you have the material sampling free energy, trying to minimize the free energy, and it's probing the free energy space due to these thermal fluctuations, so we can find the minimum free energy. Right, so these thermal fluctuations, and this is kind of a mapping of the temperature in a 2D space, showing this kind of fluctuation. Right, so how does that pan out for a polymer? Well, polymers chains are always moving around. And so they're gonna have So normally you think about entropy, like if you have a gas, right? Gas atoms moving around. Each one has like kT energy, so it's got kinetic energy associated with it, and that gives rise to this entropy, right? S is going to be related to Q by T, the heat of the system by T, or it's going to be the free energy of the system. It's going to be this entropy, which has to do with kind of the disorder of the system times the temperature, the negative of that plus the enthalpy. Right, so you have kind of the energy that you can measure for the system. It's going to be composed of this kind of randomness term and this energetic interaction term. Right, so that's why everything doesn't collapse to just a perfect crystal. Like enthalpically, everything in the world would just collapse down to a perfect crystal where it reaches the minimum energy. But because there's entropy and temperature, things can take different shapes. They can take a liquid form, a gas form. Right? So basically this entropic part is governing all the differences you see in the world. Otherwise, everything would be the same. It would just be a collapsed state. Right? So you need this entropy to drive it, and that entropy is driven by this thermal fluctuation. So in terms of polymers, we're looking at thermal fluctuations of a chain, and in terms from a physics perspective, a chain is just a bunch of connected dots. Right? So something like this gas, but if you could connect the dots in the gas with covalent bonds, then you'd have this chain structure like that. Right. So this kind of thing is a random walk, like a Brownian motion. So you can think of if you have a dust particle, and the dust particle is being bombarded by gas atoms that each have a kT energy, and they make the dust particle move around. Right? So the dust particle is going to take random steps in random direction. The average position of the dust particle is going to be 0. So, but it will trace out a pathway that has a mean squared path. In other words, if you take the square of that distance, is going to be basically the time that is diffused times the diffusion coefficient. Right. So the mean size of a dust particle moving in space is going to be related to the time. The mean size is going to be related to the time, the square root of time. So that contrasts, that's diffusive motion. And the other type of motion is ballistic, like a bullet, so that the R goes with T. So this is a root mean squared position of a dust particle. And so the polymer chain is going to ideally behave that same way. So I can show you how that works. So this is a program, right, that takes, so the top part is to make it run, and the second part says, I'm going to start at 0. Then I'm going to each time I go through, add a link to the chain. I'm going to either make it go in the X direction, in the minus X direction, in the Y direction, in the minus Y direction, in the Z direction, and minus Z direction. And I'm going to repeat that for 10,000 times, right? And then I'm going to make a chain. Right, so this is a chain that could make. So you can see it's got no obvious shape to it, but it isn't. So if you say, well, what's the size of this thing? This R squared number is going to be like a useful parameter, because the average, if you take a lot of these chains and take the average R, it's going to be 0, because it's random. It's randomly going up or down, left or right, in or out. So on average, if you average up all those random steps, you end up at 0. So the average position would be 0. So that number is useless. It's the only number that's of value, the lowest order number that's of value, and the only ones that will be of value are going to be even order moments. So even or the first moment would be the root mean squared position, which by diffusion goes with time to the 1/2. And since time, in other words, because we're taking steps and each step is equal time, then basically this would be the number of steps to the 1/2 would be kind of this average size, right? And the prefactor of that which is the diffusion coefficient for diffusion, is this something called the Kuhn length, which is the step length. Like how long is that step between these points? So that gives us this kind of measure for what a polymer would look like on average. And so this is an average. It's a numerical average of the square of the distance for the chain. And so you can see what happens here when you do this. So I just run that program. So I'm doing a 10,000 step chain, and I'm going to do one chain. So every time I do it, it will look quite a bit different. Right? So generally asymmetric. So generally it's going to have like some kind of, this is a typical polymer. This is like polyethylene would look like this. Right? If you could pick out one chain of polyethylene from a milk jug. So it's going to have some kind of asymmetry to it generally. Sometimes it won't be asymmetric. So there's some possibility that would always stop. So it would have like zero size or size of LK. Like in other words, it would just go forward, backward, backward 10,000 times, and it would just be one spot. So there's a minimum size that this R squared 1/2 like could be between 1 or between LK and then 2 like N times LK, the extended length, the contour length through the chain, right? Sometimes called capital L. I see you have that kind of range of possibilities for this size, and the average of that is going to be LK times the square root of N. And you can see like this, you can do this a bunch of times and see. So, so if you do it one time, so this is giving the number of steps is over here, and the step length is 1. So, and this is giving R squared. This 50,337 is calculating R squared. Oh, wherever that program right here. So it's printing out for the endpoint. What is the sum of the squares divided by the number of chain steps? So that would, this basically gives you, so the sum of, divided by the number of chains, this gives you the average R squared for the chain system, which should give you the average R squared. If L is 1, should give you N, right? So R squared of 1/2 is N to the 1/2. R squared will give you N. Right, so these two numbers should be equal, but for each one that you do, see, they aren't equal, right? Sometimes it's larger, like 109,418 to 100,000, and then 28,000 to 100,000. This time was 50,000 to 100,000. So in order to get that number, the point is that one independent chain isn't going to tell you much of anything, right? It's not going to tell you the molecular weight of the chain. So you need to look at a lot of chains. And so say you could do this thing like 100 times. So it's going to just make 100 of these chains. And you can see each chain is completely different. Right? There's no uniformity to it. Some are long, some are short, some are tall, some are wide. It's like the Dr. Seuss thing. Right. So this is just making 100 chains. And then at the end of making 100 chains, it'll spit out what the average is, and hopefully the average of this R squared is going to be the N, showing that this function kind of works. It's a little bit slow, I think, because it takes time to display the thing. Anyway, so that's like a physics way to describe what a polymer is. A polymer is going to behave this way, like a randomly ranged polymer is going to behave with this this kind of root mean square goes with N, goes with the molecular weight, and that's going to be called a Gaussian chain. So you can call that a Gaussian chain, which I'll tell you why. It can be called a Brownian chain. So Brownian chains because it looks like diffusion. Can be called a random walk. So there's a bunch of different words that describe this same thing from different perspectives. In other words, Brownian chain means you're looking at a diffusion analogy. Gaussian chain has to do with the statistics of this distribution of these end-to-end distances. So if you plotted out this end-to-end distance, it can go from LK to NLK. So if I say, what's the probability of finding an end-to-end distance R? And again, this is really the root mean squared R, but versus R. So you have R would be 0, and the maximum probability would be at 0. Okay, then the probability of this thing. Okay, so it finished and it got, so for 100 chains, it got an average R squared of 114,000. And then the n that was put in was 100,000. So if I did enough of these, I would get exactly 100,000 out of this. Right? In other words, I would get exactly that R squared average equals the number of units, which is 100,000 times LK squared, and LK is 1 here. Right, so that would work out if I did enough of these chains. Right, so anyway, so anyway, that's kind of give you a feel for what this looks like. All right, so I can make different chains, but thermally these things are moving around by KT, so there's thermal fluctuations in this. So each of these different structures can exist for the same chain, like they'll be moving all the time thermally. So you see this isn't just a collection of chains. It could be one chain moving. It could either be a collection of chains or it could be one chain just thermally moving to explore this kind of entropy space. So the more random this is, the higher the entropy. So if this is all collapsed to one spot, so you have one state, then log of 1 is 0, so it has 0 entropy, 0 configurational entropy. And then if this is fully stretched out, it only has one state. So that has also log of 1 is 0. So the entropy, Boltzmann's law is going to be ln of the number of states. Right? So ln of omega times k, Boltzmann's constant. Right? So if you have one state, there's no entropy. Ln of 1 is 0. Right? So the position that has the maximum number of states is going to be this mean square, this number. Like when it has an end-to-end distance of L n to the 1/2, that's when this would have the most number of states. If you look at the probability of any given state, right, it's going to truncate. Will truncate at NLK is the maximum, and then it's going to have a peak at 0, and then it's going to follow Gaussian with a bell-shaped curve. And it's going to look like that. So you'd say the Gaussian is going to be exponential minus whatever R value we have over this root mean squared value. 2 NL squared if it's a 1D thing, and then 3D it's 3/2 NL squared. Right, so that this P of R is going to be proportional. This would be a Gaussian. So it's R squared over it. So this would, for 3D Gaussian, this thing is exponential minus x squared 3/2 sigma squared. And sigma squared is this root mean squared value. Right, so that's why this can be called a Gaussian chain, because the shape of that probability function for these end-to-end distances is Gaussian. So let me get this in here. Okay, so any questions about that? Hopefully that's kind of clear. This is one of the basic things in the course, like this idea that the chain follows this distribution. That's the Gaussian idea. So there's other ways to talk about what a polymer is, right? So how to define a polymer. So from a perspective of crystallinity, right? So basically, if you take alkanes, I think I talked about this a little bit, but if you take, maybe I didn't. So you take like ethane, and then you take propane, and you take butane. So these are, if you're not a chemist, these are, I'm not sure this will help, but these are like these kind of units, right? Hydrocarbon. So this is two carbons with hydrogens. Carbon has tetrahedral, so you have 6 hydrogens, 2 carbons. This propane would be, so I just put a line for hydrogen, right? And then butane is 4. Right, so you have these ethyl units, and butane's the first one that has like an ethylene unit. Let's see. So you have this ethylene unit, C2H4, and then it's got methyls at the ends. Right? So that's butane. Pentane is just add another one. So these are the alkanes. So polyethylene is like this thing to the N, and then methyls on each end. And N is going to be 100. So, right? So that'll give you a chain of about 100. In our simulation, thing, 100 chain would look like this. Like, just do 100. So it's going to be a small chain. So that's 100 chain. But it still acts like a polymer when it's 100. 10,000 is a lot, but 100 is kind of the cutoff point more or less for polymer, right? So all these things crystallize. Okay, so they'll crystallize into this. So this is looking down the crystal lattice, and the AB, and the C direction is into the paper, which would be the chain direction. So like if you look at this thing this way, you see that this projects into a straight line. Each of these straight lines is one of these chains going in, and all the alkanes crystallize kind of in that way. It's an orthorhombic crystal. And so A, B, and C don't equal each other. And C is basically a unit, a monomer unit length, which is like 2.5 angstrom. So anyway, so that's kind of the, so if you look at the melting point of these things, the alkanes, so here you have methane, ethane, propane, butane, let's see, propane, butane, hexane is 6, pentane, hexane, heptane, octane, nonane, whatever. Dodecane is 12, right? So anyway, so it's a straight line. So you have basically going with the melting point is just proportional to the length. So the more, in other words, as you add more of these monomers into it, then you get more enthalpy. The enthalpy just goes with how many, right? And this jog of up and down is that the even and odds will do this kind of weird jogging thing. So the crystal for the even and odds, one goes like that and the other's just straight out. Okay, so the difference in the melting point is because there's a jog in the crystal face for the twos, for alkanes, right? So it has like up and down, not up and down, but it's like a jog in this. Then once you reach a certain point, that jog doesn't matter anymore because the overall enthalpy is much larger than that jog difference. And then it just smooths out. But then a strange thing happens, it doesn't just keep going up. Right? When N reaches about 100, which is something that would look like that, right? So some fairly small chain, this thing tails over and reaches a plateau. Okay, it reaches a flat point. So that's a little odd. So this point of 100 is about where you talk about a polymer. This is defining a polymer in terms of the melting point of the crystal. It reaches a constant melting point. doesn't matter if you have 1,000,000 molecular weight or 100,000 or 10,000, it's going to have the same melting point. Okay, so this is a signature that something happens in the crystal related, and it has to be kind of related to this chain entropy, like this conformational business. So basically, what's happening is the chains start to fold. So for the alkanes, we had the thing stacked up like this. Once you reach polymer over 100, they can do this. They can like fold back and forth. Okay, so they do kind of a knitting thing. Okay, so the crystal in this region, and this is the boiling point. The other thing is that the polymers, high molecular weight polymers, don't boil. Like they have too much of a, or the degradation point is going to be like 350. So you can't heat it above that point, it would burn. And also you can't really make a vapor out of a polymer. Right. So basically there's a cutoff point here and boiling point. And also there's a cutoff point in this melting point because you get this plateau showing up. Right. So this is what these crystals look like. Okay, this is that same plot, and it's just showing some things from, this is from this book. It's on the web page. So this is from this book, probably clicked here. This, where's that book? Bauer Polymer Crystals, Engineering Aspects, 2001. It's from this book. Okay, if you click that and put the FN for PDF at the end of it. So let's see. I think it's from this book. So you have to put the FN at the end. F. That should get the book. Right? And I think it's chapter 5 in this book. It's basically chapter 5 in that book. You can find these pictures. So this is a single polymer crystal, right? And in dilute solution, they'll form these kind of platelet-like crystals that actually form a pyramid. You can see here. And within that pyramid, the chain is folding like this, it's knitting through the crystal. And that can be shown with TEM and also electron diffraction of a local region in this. So you can demonstrate that this is happening. And then the thickness of this thing, you can see 15 nanometer, right? So basically this going to ask from 2 micron diameter. This is a 1 micron line. So this has the aspect ratio of a sheet of paper, except down to nano scale. So it's like a nano sheet of paper. Okay, so it's kind of an odd crystal. Okay, it's because this fold energy, the aspect of this thing is going to be related to the energies of the surfaces, and this fold surface has a huge energy. Right? It's got a large energy. In fact, the fold surface energy is about 2 × 5 joule per centimeter squared. All right, and the enthalpy of melting per cubic centimeter for the crystal, so within the bulk of it, is 300 joules per centimeter cubed. Right, and if this crystal wasn't folded and was an alkane crystal, fully extended, which you can get by changing the crystallization temperature, I mean, you can extrapolate it, it would have a melting point of 141 C. Okay, so the melting point is going to depend on the thickness of this thing. So you have the thickness of the crystal. The thickness of the crystal is going to be related to the energy of that fold. There's 2 surfaces, it's 2 times that fold, and then delta H at fusion for the bulk part of the thing. That's the bulk part. And then this infinite, if the thing was a fully extended crystal, the melting point, and then that melting point minus the actual place where it was crystallized. This is called the Gibbs-Thompson equation. And you get that equation by just saying that you have the volume, you have the enthalpy of melting and the entropy of melting, and then you have the surface energy term times the area, and there's two surfaces to it, and that gives you the Gibbs energy of melting. At the melting point, you set that to 0. The area divided by the volume gives you the thickness. This thickness, or the volume divided by the area gives you the thickness. Then the if it's an infinite crystal, so for T infinity, there's going to be delta H over delta S. So you can substitute in T infinity and just have delta H here, and then you can get this equation pretty quickly. Right? So this is a pretty simple equation to describe this. So if we plug in the numbers for that, say it was crystallized at 110 C, which is normal temperature to crystallize polyethylene, then you find out that you have 17.8 nanometer thick crystals from that equation, using those kind of rough numbers. And here he's got, like in this micrograph, he's got 15 nanometer thick. So it's about the same number, right? So anyway, so that means that this doesn't matter what molecular weight it is. It's just going to fold that way because of the ratio of the surface energy for a fold and this bulk enthalpy for the crystal, right? So you get a plateau out, and the plateau happens where it's a polymer where it can fold. It's the idea, can it fold? If it can fold, it'll form this kind of crystal, and it'll have a range of melting temperatures that are related to this thickness of the crystal. So this is pretty important because this kind of bending of the chain allows it to entangle with each other. It means you can make these crystals that are platelet shaped, and you can also have them hooked together because they can entangle between the chains. You can make a robust material with that afterwards. And that's true of all polymers, right? All polymers that will crystallize. Sometimes they can't crystallize because side groups won't allow them to crystallize. But basically, for ones that crystallize, the engineering properties come from this ability for the chains to bend like that. Okay, so anyway, so I already, this is the viscosity thing I talked about. So there's a 1 over gamma dot here is going to give you a relaxation time for the material that says when you're deforming the structure of the polymer chains, and only long high molecular weight polymer chains are going to do this kind of deformation that leads to a reduction in viscosity. The other part of this curve is this zero shear rate before you deform. So when you're well below the this relaxation time, then you get a viscosity for the undeformed material, right? The zero shear rate viscosity. And that zero shear rate viscosity depends on the molecular weight. And if you're at low molecular weight, so in a oligomer, that viscosity, so that viscosity is going to be like a drag coefficient. It's going to be something like a drag coefficient. And so basically, if I have so you can think of it like trains, right? So higher molecular weight means more cars in the trains. This drag coefficient goes up, and it should be proportional to the ends, to the molecular weight. But if the trains start to entangle, so if this thing has some kind of coupling to other trains, then there's going to be a much stronger dependence on molecular weight. And at that point, this thing is going to go with the molecular weight to the 3.4, roughly 3.4 power. So steep dependence, right? So you can see this log plot of this plateau viscosity versus log of the molecular weight. There's a transition point, which is the entanglement molecular weight, the point where the chains can start to interact with each other and form a network. So above that molecular weight, it's the entire sample at some time scale below this tau star, below this gamma star, is going to be a single gel. It's going to be a single molecule. And above that time, when it can't relax anymore, then it's going to be multiple molecules. So the viscosity drops. And so if your whole sample is one gelled chunk, then it's got a high viscosity. When it starts to be able to relax, when it starts to not be able to relax, so it remains straight and unentangled, then the viscosity drops dramatically, right? So in this cutoff, this kind of behavior only happens above this entanglement molecular weight, where the plateau modulus shows a strong dependence on the molecular weight, power 3.4. Right? And you can see the same thing in solutions. When you get to low concentration solutions, the viscosity is proportional to the concentration. And once you get above a point where they can entangle, then you see a strong dependence of the viscosity on the concentration, which is, this is also log, so slope here is also something like 3.5. and the concentration thing.
Hey, Dr. Beaucage.
Yeah.
Well, actually, you may cover it here. I was going to say on the zero shear portion of the curve, would that be, can you define if that's driven by the storage or the loss modulus of the polymer based on that curve?
Well, the viscosity, this is really just the loss modulus part of the curve. So
Okay.
the viscosity is going to be kind of related to the loss modulus.
Okay.
So, so this isn't actually time dependent though. So this is basically a continuous. So you can get this viscosity from the loss modulus, like G double prime times omega is proportional to the viscosity, this same viscosity. So I'll talk about what G double prime is in the next slide. But so basically they are related, but this measurement is a continuous. This is kind of looking at you can get this curve from the oscillatory measurement, but basically the way this is being looked at here is if it was a continuous measurement. So you just have like a force. So you have your two plates. So you just have a force and an area normal to it. And then you have this velocity gradient. Right? So you have gamma dot, and it's just running continuously. Right? So it's gamma dot, and the tau is just the force that's being put on the top plate. And then the viscosity is just the thing that relates those two. Right? So yeah, in this case, you can get the same information from oscillatory measurement, but the way this is looked at here is just a continuous measurement, like it's just a continuous turning of you have the disc cone and plate, and you're just continuously turning this thing in one direction. It's not an oscillatory.
Okay.
And it's pretty confusing. I mean, there's a lot to it. Like you can do a whole course just in rheology, right? But basically, I think you roughly get a feel for it, and that's all you really need right now, you know. So yeah, the two things are related, but it's really drawn a line between the two when you're at this point of it. There's a lot of other behaviors. The shear thickening too, like in eggs, when you whip up egg, you can get an increase. That's also due to structural changes in the fluid, but that's kind of a permanent structural change, and the thing becomes a gel when you denature the proteins. I was in that case for eggs, so you basically have a long polymer chain like egg albumin, right? And then when that's in the native state, it's folded up into a little box. So native state proteins kind of collapse down into a structure, a dense structure, 3D, right? And then when you whip it, it becomes this polymer chain. When it becomes a polymer chain, they can entangle. And then when they entangle, you can make egg froth from it, whatever. You know? So basically, by mechanically destroying or breaking apart the protein, the folded protein to unfolded protein, you can get this kind of gelling of the thing. That's called shear thickening. So the more you shear it, the thicker it gets, but it's not reversible. You can't unfroth an egg. You can't. It's almost like you've destroyed life. Like this is life and this is death, and you can't make it back alive again. But I mean, you can theoretically, you could, but basically you can't. But once you, so shear thickening usually is a one-way street. Shear thinning, on the other hand, because you're straightening it out and it's like a spring and it springs back, it's reversible. Okay, so there's different rheological phenomena. Some are reversible, some are not. I mean, you could think about, like, you could have shear thinning if you ripped apart the polymer chains too, and that would be not reversible. So if you actually degrade the polymer in the rheometer, that would be a non-reversible shear thinning, or if you burned it while you're measuring it. So anyway, this is another way to describe polymers. Okay, so this is actually the typical way to look at the oscillatory rheometry measurement. Right? So you say if you just get rid of that. Any other questions on that stuff that what I just did? All right, so if you take a rubber ball, right, you drop it on the floor. Sometimes they do this in class, and then it bounces back up, but it won't bounce back up all the way. Right? So you say like it has this response, like it had a force of impact, and then it has a elastic response. And there's this part that's like missing. That went off to heat. So that's a viscous response. So it's got a viscoelastic response. It's got like this you'd call G prime, and whatever's left you'd call G double prime, the loss part. So you have storage, you have loss. Right? Turns out that as you change the temperature, so if you can, this thing will form a glass at some point at the glass transition temperature. If you reach the glass transition temperature, this rubber, so the rubber itself is a bunch of chains that are hooked together by crosslink sites. And the reason that it has elasticity is because each of these chains wants to form that random walk we looked at. And when you deform it, it forms something a little bit straightened out, and it wants to spring back. Right, so that's why it has this elastic modulus associated with that deformation behavior. Right, and the storage modulus, the loss modulus is going to be due to kind of flow of the thing. Once you reach the glass transition temperature, this thing will just be all flow. Like it'll just totally stop when it hits the bottom. Okay, so at temperatures above the glass transition, these chains have motion, and they allow this elastic behavior. At the glass transition, the energy is completely absorbed. And below the glass transition, these things are frozen. So it acts like a rock, and it has kind of non-viscoelastic behavior. It just has a storage modulus. It just bounces like a crystal would, like a metal ball would bounce. Right? So just so you can look at the bounciness of this, you could take the G prime divided by you take G double prime divided by G prime, and you call that tan delta. And that would be like a measure of kind of, if you plot it across temperature and a TG, you would have like a maximum. Right, so you can plot this kind of behavior in complex space. You could say G double prime is an imaginary number and G prime is a real number. And then you could have a point where you are in that space, and this angle del would be the angle between those two, and then tangent of the del is like the ratio of those two values. It gives you that point. Right, so they talk about this tan delta for the things and measure this kind of loss. Anyway, as you change, so temperature and frequency, because the temperature has to do with how fast these chains can kind of relax out of their state. Right, and the frequency also has to do that, because we know that if we plot log viscosity, log frequency, we have like a viscous region at low frequency, and then it has a region where it's deforming. So that's like almost like a solid. And there's this transition point at this tau, 1 over tau, for the transition of the thing. So basically, this is gamma dot. So there's the derivative of the strain rate. So we can plot versus frequency. It's something like going through temperature, like there's an equivalence between the two, because we have that the viscosity goes with an Arrhenius kind of behavior, like an activation energy divided by KT. So there's a relationship between the viscosity and the temperature, and there's also a relationship between the viscosity and tau. So tau goes with temperature. So time and temperature are related by an Arrhenius equation, Arrhenius function. Right, so basically, you can plot out this versus frequency. It's like looking at temperature, and high frequency is going to be low temperature, and low frequency is going to be high temperature. So it's like an inverse plot here. And it's usually a log-log plot, so you get power loss out of this. So if you plot the storage part and the loss part on a log-log plot, you find out that it's at low frequency, so there's a lot of time, it's going to be a liquid. At high frequency, it's going to be kind of a solid, right? So basically, if you look at the G prime curve on this thing, it goes up, and then it reaches a plateau where it's acting rubbery. Okay, that's called a rubbery plateau, and that's related to the molecular weight between entanglements. And then at low frequencies, it's a liquid, so G double prime is larger than G prime. And there's what's called a crossover frequency. And that's the frequency where it goes from behaving like a liquid to behaving like a rubbery solid. Right, and at higher frequency, there's another transition that has to do with the structure. So also this has to do with the size scale. So high frequency, if you think of bells, high frequency bell is small and a low frequency bell is large. So high frequency has to do with small things. So you're looking at smaller features of the structure here. And this is basically the Kuhn length. This is another crossover where it starts to, the flow part of this loss modulus becomes larger than storage, and that happens at the Kuhn length. So it's two crossover frequencies in this curve. Only one of them can usually be experimentally observed. And that crossover frequency has to do with the this relaxation time, where the chain can relax, it can flow below that, and it can be solid above that. So there's different ways. This only happens with polymers. So we're out of time. So so next time I'll find a paper for the homework, and I'll kind of go through a paper on these subjects roughly, or maybe a couple papers, and then I'll kind of talk about that, and I'll try to get it to you before class so you can take a look at it, and then hopefully you can ask questions, and I can kind of go through what's on the homework. Then the homework will be due, I guess, Sunday night at midnight or something, or before class, because on class on Monday, I'll go through the homework again, like whatever the answer is. And then we'll do that, kind of repeat that. And again, it'll be broken up into groups of 2. So I'll split you guys up into 2, and I'll couple the undergrads and grads with grads somehow. So any questions or anything? So I'm over time now. So if there's any questions, let me know.
See you Friday.
Okay, see you. Yep. See you guys later.
Dr. Beaucage, could I talk to you after class?
Yeah. For Khan to leave. Okay. It's not. Yeah, so what's up?
So I was wondering, so do we have a quiz on Friday?
It's not a quiz, it's a homework.
Okay.
So it'll be partnered with somebody.
Got
and then
it.
like two grad students, and you're a grad student, right?
Yes, but I have a very low background. I've done more of the testing. I haven't done most of the theory.
Yeah, I think it'll be okay, I mean, I don't think, anyway, we'll see how it goes. Everyone's gonna get an A or a B first off, so you don't need to worry much about the grade, hopefully with the pairing up, oh, here, let me stop a minute. This thing is still recording.